An introduction to voltage controlled oscillator. I remember I gave an introduction to this earlier. We had a discussion about voltage controlled oscillator. So what happens here is you have the antenna first in the receiver circuit. We have the antenna. After the antenna, because the antenna receives the signal which is very low, the amplitude of the signal is very low. So therefore, after the antenna, there will be the LNA, low noise amplifier. So that will amplify or boost the signal. Then that is RF signal, radio frequency signal. From the RF signal, we have to get intermediate frequency signal, for which we require that RF signals will be mixed or heterodyne with a local oscillator or signal from the local oscillator. The local oscillator signal is generated by VCO. These things we have already discussed. So the VCO design issue is its tuning range is small, not very large. So it has a small tuning range. So that is one. So you need to cover all frequency channels within that tuning range. So the tuning range should be such that all frequency channel is to be covered by the voltage controlled oscillator. Then the noise due to this VCO, that will impact receiver sensitivity or performance. If there is noise, higher noise will impact more. So noise should be less. Then power, you require low power dissipation. So that is the power. Power issue is low power dissipation is required. Isolation, it should be isolated from other circuits, otherwise its performance will be affected. So you want to minimize the noise pathway into the VCO, or you have to isolate it from other circuits. That is what is the noise comes from the other circuits. Then it should be less sensitive to the process or temperature variations. So it should be more stable with respect to the process or temperature variation. So that will make it manufacturable in high volume. Otherwise, if it is very sensitive, then high volume manufacturing will not be possible. So what we are basically looking at, or we are discussing, is the IC, VCO IC, design of VCO IC, or what is a VCO IC, what is inside the VCO IC. That is what we are going to discuss. We are designing a VCO IC. So the design issues for the VCO ICs are this that we discussed. Now, on VCO design, if you have a broadband high-speed data link, in that case, how do you design the VCO? Look at the figure. In the figure, you can see that to the mixture, before the mixture, you have the broadband transmitter. So from the broadband transmitter, and then you have a PCB board trace. So through the transmission lines or the traces on the microstrip lines on the PCB board, these are connected to the interface package. The package is connected, the output of the package is connected to the amplifier with input impedance Zin. Then the output of the amplifier is the boosted version, or the boosted power that has come from the broadband transmitter, that is boosted by the amplifier. That goes to the input of a clock and data recovery circuit. So there will be a circuit which is a clock and data recovery, which means whatever data, input data is given to this as input, that data will come out as the output. So data is recovered. That is what is data recovery. Then the second thing is, from the input it will generate a clock. So it will generate the clock pulses using the, so it will act as a clock, and the clock pulses will be generated because of the input. Once the input comes here, that will generate the clock pulses. So the output of clock and data recovery circuit, there are two outputs. One is data that is coming in, that will come out, input data will come out as the output data, and the clock will be there. CLK is representing the clock. So the data within the data recovery circuit. You can see there is the data in, then it will detect the phase, and from the phase detector you will take the data output. So data input and data output will be the same. Input data will not change, it will be the same, only change is the phase. Because of the path there will be some change in the phase. Except the phase change, the input data remains as the output data. Then it goes to the data goes to a loop filter. From the loop filter it goes to a VCO, voltage controlled oscillator. The output of the voltage controlled oscillator again comes back as the feedback to the phase detector. So the phase detector detects the phase between the data input and the VCO output. That phase will be detected. That will detect the phase. Accordingly, you will get it will go to the loop filter. It will filter out the out of band signals. In the loop filter, it will filter out the out of band signals. Then it goes to the VCO. So the VCO output will be clock pulses, almost clock. You can see the red one, which is like clock, although it is not exactly square, it approximates the square pulse. So in designing this, the issues are the same as the wireless circuit design, same issues as the wireless circuit design, same issues prevalent here. But in addition, noise performance to be less stringent, you can relax the noise performance consideration here, and tuning range is usually narrower compared to the RF or wireless design. Now let us look at some of the popular VCO structures. There are two VCO structures which are very popular. One is LC oscillator that we have discussed earlier. In the LC oscillator, as you know, LC circuit is a tank circuit, so it is a resonant circuit. If you can excite the LC circuit, it will resonate at the desired frequency, and the resonance can be varied by varying the capacitor. So that type of, by varying the capacitor, you can vary the resonant frequency. That acts as a LC oscillator. Similarly, there is a ring oscillator in which we have a ring circuit, so amplifiers are connected in series or cascaded amplifiers. Output is given back with a phase difference of 180 degree, but without any amplification. So amplification is 1, phase difference is 180 degree for the feedback. So feedback comes from the output, amplification is 1, phase difference is 180 degree. If you give that feedback, it will continue. It looks like a ring. As you see, it is a ring. The input goes out, then comes back with same amplitude, then goes out, comes back with same amplitude. So gradually the amplitude will grow because feedback is -1. So it will cancel out the amplitude at the input part. It will cancel out and it will limit. So ultimately you will get an oscillator. So this is called a ring oscillator. The LC oscillator, the top one, it has low phase noise and it requires larger area. Whereas ring oscillator, it is easy to integrate and it has higher phase noise. We will see that we will require only the LC oscillator for our study. Ring oscillator we will discuss, but it is not important for high-speed circuits or RF circuits. Ring oscillator is not important. Then, since we are considering oscillator, which means it is associated with oscillation, and we will consider the condition for oscillation. Now, what is oscillation? What is the difference between oscillation and amplifier? Hopefully, you have read it earlier. The amplifier, for stability of the amplifier, what you usually do is take the output of the amplifier, a portion of the output of the amplifier is given to as input to the amplifier. So suppose amplifier has gain A portion of it will be given to it as feedback. So the amplitude of the output, or whatever is the output, that will go through another amplifier with gain B. So that gain B will be with gain B, it will be given as input to the first amplifier on the original amplifier. So that you can see here, H j omega is the transfer function of the amplifier. So let us say that is the amplifier. Okay, to that we are giving some input X. X input is coming there. That goes to the H omega. Output is Y. A portion of Y is coming back and given as input to S. So now this will be acting as an amplifier, good amplifier, so long as the feedback is negative, which means the phase of the feedback is 180 degree out of phase from the output. Output and the output of the amplifier and output of the feedback circuit are 180 degree out of phase. If they are in phase, then there will be growth. The oscillation will grow. That we will discuss later. The oscillation will grow. Because oscillation will grow, there will be oscillation. The signal will grow, which means there will be oscillation. Now you can do that by finding out what is the gain or the closed loop transfer function. Find out what is the closed loop transfer function of the circuit. That will be Y by X, Y upon X. Now what will be Y upon X? Y upon X will be H divided by 1 minus H. J omega I am not mentioning, if that is understandable. So I will not mention J omega. So G is equal to H upon 1 minus H. This is the criteria. If this criteria is satisfied, then it will be oscillating. For self-sustaining, once the oscillation has started, now to sustain the oscillation, for the continuation of the oscillation. Sustaining means continuation. So for continuation of the oscillation, or self-sustaining without any, self-sustaining means continuation of oscillation without any external interference. So it will, on its own, it will sustain, or on its own it will continue to oscillate. So self-sustaining oscillation at the frequency omega 0, oscillating frequency is omega 0. That is possible only if H is equal to 1. If H is equal to 1, then G is equal to infinity, which means closed loop transfer function becomes infinity. Under that condition, it will oscillate. This amounts to two conditions. Gain is equal to 1 at frequency omega 0, that is the condition 1, because H is equal to 1 means gain is equal to 1. Then phase is equal to n into 360 degree, where n is equal to 0, 1, 2, etc. On n into 360 degrees. So at the frequency omega 0, these are the two conditions. Now let us consider the case of a ring oscillator. If you are considering a ring oscillator, then the number of amplifiers that we use is always odd. Gain is set to 1 by saturating characteristics of the inverters. Now look at these three. Here we are using three amplifiers. So amplifier A, then amplifier B is 180 degree out of phase with A. So you can see the signal is inverted in B. If you look at the right hand side signal picture, so B signal is 180 degree out of phase, it is inverted. Then C is again 180 degree out of phase from B. So B is 180 degree out of phase from A, which means C and A are in phase, so 360 degree. So again B is inverted. Then again A will be inverted with respect to C. From when you take the output of the C, that is the inversion. Now then also you can see that there are these signals. There will be delay between A to B because of path. there will be delay between A to B, B to C, again C to A. Those delays will be there. Those are shown in the figure, that when there is delay and what is the delay that is shown in the figure. Those delay amount is delta T, which gives rise to a phase difference of delta phi. Odd number of elements is used to prevent the stable DC operating point. So that is why you require odd number of elements. If you use even number of stages, then this stability will be lost. The phase, ultimate phase is 360 degree. So at the oscillation frequency omega 0, 180 degree inversion, then another 180 degree inversion from gate array, 180 degree inversion at the feedback, 180 degree inversion from the gate array. So suppose there are n number of stages, each with the phase shift delta phi. So then n into delta phi should be 180, or delta phi should be 180 by n. So instead of phase, if you go to time, then for time we will say n stages, each stage with time delay delta t. So n into delta t will be 180 degree, equivalent of 180 degree in terms of time period is t. So the total time period is, if it is total time period is t, capital T corresponds to 360 degree. So 180 degree corresponds to t by 2. So n into delta t is equal to capital T by 2, or delta t is equal to capital T by 2 divided by n. Also accordingly we will determine what is the number of stages. Once you know what is delta t or what is delta phi, then you can find out what is number of stages, or if you know what is number of stages, accordingly you can fix what will be delta t or what will be delta phi. So there are some other information on this ring oscillator. Due to their relatively poor phase noise performance, as I told you, one of its characteristics is a poor phase noise performance. So because of poor phase noise performance, these are very rarely used in the RF system. RF systems avoid the ring oscillator, but ring oscillators are quite often found to be in high-speed data links because they do not use RF systems. So therefore, what we will do is we will focus on LC oscillation in our discussion today. We will not look into the ring oscillator. If you want more details on the ring oscillator, you can look at these two references. One is Manetti's his paper of 1993, or look at the thesis, PhD thesis by Huygens. His PhD thesis is available at University of Berkeley. So look at the Berkeley University website. There you will get this PhD thesis. There also you can get sufficient knowledge on ring oscillator. Second is the LC oscillator or resonant based oscillator. So at the top figure shows us the equivalent circuit of an oscillator. So in the equivalent circuit, what we do is we have an amplifier which is outside the dashed region. That part is the amplifier with gain 1 and which inverts the input. So phase is inverted. If the input and output are 180 degree out of phase in the amplifier, gain is 1. That amplifier is there. The input to the amplifier comes from a tank circuit. The tank circuit is RP, CP and LP. These are connected in parallel. So that is the tank circuit. Its equivalent, you can see the equivalent of this circuit is equal to the circuit given below. So -1 is given, the inversion is given as a box. So -1, that is a block. Then output of that is Vx. So Vx goes to Gm. After the Gm it goes to Z, which is the tank circuit. Then the output of the tank circuit again comes back to the unit circuit, unit block through a feedback loop. Okay. Here, if you use the Barkhausen criteria for oscillation, then gain H is equal to G into H, G into Z is equal to H is equal to 1 for which is the Barkhausen criteria. So G into Z is equal to 1, that is the Barkhausen criteria in this case. Now if G into Z is equal to 1, and if we assume that the transconductance is purely real, then the impedance has to be purely real, because multiplication of two quantities is a real quantity provided, and one of the quantity is real, means other quantity has to be real. So assuming Gm to be pure real, J omega must be also real. So let us say J omega is equal to Rp. So Gm into Rp is equal to 1. That is, this is the Barkhausen criterion for oscillator, for resonator based oscillator. This is the criterion. Now let us look at what happens inside the tank circuit. So in the tank circuit, if you draw the curve of the tank circuit or the characteristics of the tank circuit, look at the curves that is drawn here, the top curve and the bottom curve. In the top curve, we see the amplitude of the Zj omega. So Zj omega variation with omega. So that is going to a peak value Rp at some frequency omega 0. That is the resonant frequency. And exactly at that frequency, the phase part, which is the bottom one, that is 0. And before that frequency, it is inductive. After the omega 0, it is capacitive. So if you, for parallel resonators at resonance, this looks like a resonator, pure resonator at the resonance, because the phase is 0. Phase is 0 at resonance means the capacitance and inductance are cancelling each other, so leaving out of a resonator. So looks like a resonator at resonance. Phase condition is satisfied. Magnitude condition is achieved by setting Gm into Rp is equal to 1, that we saw earlier. Now let us consider what will be the impact of Gm. If you consider different Gm values, Gm into Rp should be 1. As we discussed, it should be 1. Suppose it is not 1. Gm is small. If Gm is small, then what will happen? So if Gm is large, then what will happen? And if Gm is equal to 1, Gm into Rp is equal to 1, then what will happen? Let us consider these three conditions. Gm into Rp is less than 1, Gm into Rp is greater than 1, and Gm into Rp is equal to 1. These three conditions we will consider. So to consider these three conditions, what we will do is we will draw the root locus plot. So if we draw the root locus plot, that will give us the view of a closed loop pole location as a function of open loop pole 0 and open loop gain Gm into Rp. So this gives us this idea. From this we will get this idea. So hopefully you know what is closed loop condition, what is open loop condition from control theory. closed loop and open loop, they come from basically feedback. If there is a feedback, output is given to the input, that is the closed loop. If there is no feedback, that is the open loop condition. So these are the two conditions that we are going to see. So as the gain GMRP that increases, closed loop poles, they will move into the right half S-plane in this case. So you can see that the poles are on the right hand S-plane, and if it is less, if it decreases, they will move to the left hand. So since we require a high value, so they will be moving to the right hand S-plane. Now let us set GM too low. If GM is too low, GM into RP is less than 1. GM into RP is less than 1. Under that condition, what will happen? Closed loop poles will end up in the left hand S-plane. If they end up in the left hand S-plane, then that is the condition for under-damped response. So if that is the condition for under-damped response, closed loop poles are on the left hand S-plane. On the left hand S-plane, this is the condition for under-damped condition. Under-damped condition means the oscillation will die out. So if once the oscillation starts, it will die out. It will not be sustained, it will be dying out. Okay. Second is the opposite case. GM is too high. So GM into RP is greater than 1. Closed loop poles will be on the right hand S-plane. If they are in right hand S-plane, then this is unstable response because the waveform will blow up. It will keep on increasing, so it will blow up. So this is also not desired. Now GM is so adjusted that it is just to the right value, or GM into RP is equal to 1. GM into RP is equal to 1 exactly. GM into RP is equal to 1. Then what will happen? Closed loop poles will end up on the J omega axis. So they will not be on sigma axis, they will be exactly on the J omega axis. If they are on the J omega axis, the poles are on the J omega axis, then the oscillation is maintained or oscillation is sustained. Only issue with this is you require GM into RP to be exactly equal to 1. So how to achieve this? GM into RP is equal to 1. In practice, how you are going to achieve this? That is the question. And let us start that with a simple circuit, amplitude feedback loop. So we have oscillator, then a portion of the output is given as feedback to the oscillator through a amplifier. So what we do is we have a peak detector. It detects the peak of the oscillator. When it detects the peak, that will give in as the input to the op-amp to the negative value or the inverting pin of the op-amp. To the positive pin, we will give the desired peak value. Whatever peak value we require, desired peak value will be given to the positive pin. Then on the output of the op-amp is the adjustment of GM. So if you look at this, one can think to detect the oscillator amplitude. From this we can detect the oscillator amplitude and then adjust GM so that it equals to the desired value. So oscillator amplitude and GM are so they are adjusted through this feedback. This GM is continuously adjusted, desired peak value is given. So peak detector will detect the oscillator amplitude. So that is so adjusted that the amplification of the amplifier is so adjusted that GM is such that GM into RP is equal to 1. That is mentioned. So by using this feedback, you can precisely achieve GM into RP is equal to 1. Issue is designing of this circuit is complex. It also, because amplifier is there, it requires power, and because amplifier is there, it adds noise. These are the issues. Now, leveraging the amplifier nonlinearity as the feedback. So instead of using the feedback, an amplifier in the feedback, use the nonlinearity of the amplifier in the oscillator, because oscillator is nothing but an amplifier with a positive feedback. So the amplifier, for that amplifier which is in the oscillator, for that amplifier use the nonlinearity of that amplifier. All amplifiers are using nonlinear devices, so use the nonlinearity of that amplifier. So that is what we are doing here. Look at the figure, above figure, top figure. If you look at the top figure, you can see on that there is some input. Now, in all these cases, you can say that why we are giving a 0 as the input, what is 0, and if you are giving 0 as the input, what is the point in giving that input? That can be the question. Now, oscillators, for the oscillators, remember this, for the oscillator there is no input. In practice, there is no input for the oscillator. Oscillator, so from where oscillator derives its input? Because there is an amplifier there, so that has to amplify something. How it will amplify something? What is that something? That something is the noise. So atmospheric noise, or when you switch on the circuit, there will be spark. Any switching on or switching off always is associated with the electric spark. So there will be an electric noise there. So from that noise, it's what peaks of the noise. Maybe very small value, but that value will be amplified by the amplifier to the desired peak value, and that will be sustained. So that is for to represent that, we show a 0 as the input. Okay. So this is there. So there is an input which is 0. Then to that input there is the feedback. Then that input goes to an amplifier, which is the amplifier with an amplification factor of 1, but phase is 180 degree out of phase. And then it goes to the normal amplifier, whose gain is GM. So GM into RP is the gain, GM is the transconductance. Then the current from that amplifier goes to the tuned circuit. The output of the tuned circuit comes as a feedback to this. So is used as the feedback. Now here what you can see is this -1 corresponds to the, it will be -1 exactly at the frequency omega 0. So therefore there it is shown with amplitude A. So the spectrum of Vx is shown with amplitude A at omega 0. That is, when it goes through the GM, the spectrum will be GM into A. At omega 0, at other frequencies, it will be something else. It will be smaller than GM into A. Practically, if you look at the practical view, practical transconductance amplifiers, they have saturating characteristics. They create harmonics, but the harmonics are filtered out by the resonator itself. The harmonics are created, but these harmonics are filtered out by the resonator itself. but our interest is in the relationship between the input and the fundamental of the output. So other frequencies we are not interested. We are interested only at the fundamental frequency omega 0, not at DC or first harmonic to omega 0 and second harmonic. All those we are not interested. Now look at the amplifier nonlinearity as the amplitude control, how the amplifier nonlinearity is controlling the amplitude. There are two figures. If you look at the figures, there are two figures, the top figure and the bottom figure. In the top figure, you can see it is the variation of I or the current with A or the amplification. So current with the amplification or voltage. It is linear over a portion, then it becomes non-linear. So compared to that, if you look at the GM, the bottom figure, if you look at the GM versus A versus GM, so then you can see that the portion over which it is linear, GM remains constant. The red picture, so the red portion of the plot remains constant, over which Ix is linear. As Ix becomes nonlinear, this GM gradually drops down towards 0, and it comes to 1 at GM into Rp is equal to 1 at a point. So that point is shown here. That is shown in the figure here on the left hand side, that is shown here. So what we say from this, what we conclude from this, that as input amplitude is increased, as you increase the input amplitude, effective gain from the input to fundamental of the output will drop, amplitude feedback will occur, GM into Rp is equal to 1 in steady state. Now let us have a look at one port view of the resonator based oscillator. Resonator based oscillator means, the moment we say resonator based, always understand that it is a LC circuit or RLC tank circuit. So what we have here is the resonator is on the right hand side, the active negative resistance generator is on the left hand side. We will see why it is active negative resistance generator. These two are on the two sides, and its equivalent circuit is shown below. Here at the bottom, its equivalent circuit is shown. So same thing. Resonator is RLC circuit and active on negative resistance circuit. So 1 by minus GM is equal to minus R, and on the out is taken between them. It is convenient for intuitive analysis. So you can immediately think of the analysis. You can immediately think of what we do here is we try to cancel out the loss in the tank circuit. Now the tank circuit consists of R, C and L. Loss will be in the R. So the R is to be compensated. This Rp needs to be compensated. How to compensate this Rp? Rp will be compensated if we have a Rp is positive. So suppose you have 5 ohm. So how do you compensate that? Means how can you make it 0? So you should have something like minus 5 ohm, a resistance of minus 5 ohm. So a negative resistance is required. So 1 by GM, conductor 1 by conductance is equal to resistance. So 1 by GM should be Rp in amplitude, and they should be opposite in value. So negative value. So the resistance should be minus Rp, which is equal to minus 1 by GM. So 1 by minus GM is equal to minus Rp. Or you can say 1 by GM is equal to Rp, or GM into Rp is equal to 1. This also establishes the Barkhausian criteria. So from this also you can see the Barkhausian criteria. Now the modeling that we saw up to now for the resonance circuit is a parallel RLC circuit. But always we may not have a parallel RLC circuit. Sometimes you may have a series RLC circuit. But the analysis for one port modeling that requires parallel RLC circuit. What is still done in this case? So look at this figure. The left hand figure is a LC circuit. C has a resistor connected to it, loss component. L has a resistor connected to it, which is a loss component. So C and L are in series. They are connected to loss components. So on this, and this is operating over a very narrow band frequency. So always we can do a parallel transformation to achieve a parallel network for the analysis. Only thing is, I remember in practice, RLC networks can have secondary or more regional frequencies, so they will not be restricted to one frequency. Since they will not be restricted to the frequency only, this may cause undesirable behaviors. And making equivalent parallel networks, they will mask this problem. If you do this problem of secondary regional circuit with secondary regional frequencies, they will be masked by equivalent parallel networks, and so you will not see that. Only you will see it only if you do a simulation. So if you do an electronic simulation using a simulator, you will see the secondary frequencies, presence of secondary frequencies will be there. Otherwise, in the analysis, you do the analysis, normal analysis over a small frequency band, then that will be masked. You will not see that. Now let us consider an example, visual example using negative resistance oscillator. Now you can see on the left hand side we have the oscillator which is in the differential mode. The circuit is in differential mode. It contains L and C. Now, the moment it contains L and C and they are in series, what you can do is, for L you can add a resistive component or a loss component. For C also you can add a loss component. So that is the equivalent circuit shown on the right hand side. Otherwise left and right are same, except on the right hand side the loss components are there. So this type of oscillator structure is very popular in CMOS implementation, because this is simple topology, simple configuration. Differential implementation is there. The advantage of differential implementation, particularly this is good for feeding differential circuits. Then it has good phase noise performance. Now what you will do in the analysis process is, first derive a parallel RLC network which includes the loss of the tank, inductor and capacitor. Typically this loss will be dominated by series resistance in the inductor and series resistance in the capacitor. In both the cases you use series resistance. Then split the oscillator circuit into half circuits. Because it is differential circuit, so each side split it into two halves. So that is what is done. In the top you can see that it is done on the left hand side only. We are considering the left hand side, and the feedback in the left hand side is -1. So that is shown here, -1 M1 -1 V out is -1. That goes as the feedback to M1 again, and the circuit is there. The tank circuit is RP1, CP1 and LP1. So that is again equivalent to for the feedback given to the amplifier that we have seen, that is 1 by minus GM1. or 1 by Gm that we have seen. So in this case, this will be 1 by minus Gm1 because Rp into Gm is equal to 1. So that from that we have seen 1 by Gm is equal to Rp. So for that, this part is minus 1 amplifier and the device that is equivalent to this minus Rp. So put that minus Rp there, that is equivalent to a resistor of minus Rp, put that minus Rp there. So it is minus 1 by minus Gm1. So if you have Gm is large, then signal transconductance Gm has to be have a large signal transconductance value. And then come to the design part. Designing the circuit again, divide it into two parts. Look at the first part, left hand part, and in the left hand part, what we have to ensure this Gm1 into Rp1 is equal to 1. That is what we have to ensure. So design tank circuit components to achieve high Q values that will result in Rp value which is as large as possible. Then choose bias current, I bias, for a large swing without going far into the Gm saturation, because if you go into the Gm saturation, then Gm into Rp will not be equal to 1. So without going into Gm saturation, take I bias value as large as possible. So we will estimate the swing as a fundamental function of the I bias circuit after this. Then choose the transistor size to achieve the adequate large Gm1. So usually this will be twice as large as 1 by Rp to guarantee the step-up. Now we will calculate the oscillator swing. What will be the peak-to-peak value or oscillator swing value? So maximum sinusoidal oscillation. To get maximum sinusoidal oscillation, what is to be done? Circuit we are not going to discuss anymore. Just look at the analysis. I1 and I2, these two should be greater than 0. I1 plus I2 should be equal to I bias. If I1 plus I2 is equal to I bias, let us choose. Both of them are going to give us sinusoidal functions and they are in difference mode. Therefore, we can take I1 is equal to I bias by 2 into sin omega 0 t plus 1. I2 is equal to I bias by 2 into minus sin omega 0 t plus 1. Now if you add I1 plus I2, that will give you I bias. Now A, the amplification is equal to 1 by 2 I bias into Rp. Now if the amplitude is very large, A is very large, we can assume that I1t is a square wave. Instead of sine wave, you can, because it is very large, so the portion over which it is nonlinear, that portion can be taken as a straight line. So to doing that, you can take it as a square wave. So if you take it as a square wave, if you assume I1 to be a square wave, then our interest is in determining what is the fundamental component in the square wave. As you know, any square wave, and that during the Fourier analysis, Fourier series analysis, you can say that a square wave is a combination of many sinusoidal waves. And when you say any sinusoidal wave, the lowest frequency is called the fundamental frequency. Other sinusoidal waves with other frequencies are harmonics. So we'll consider the fundamental. So our interest is determining the fundamental component. Why? Because at the fundamental component, the amplitude is maximum, and other components are filtered out. The C and harmonic are filtered by the tank circuit. The tank circuit filters them out. Now look at the figure. From the figure, you can see easily that the fundamental component I1 is equal to 2 by pi. Using the Fourier analysis, it will be 2 by pi into I bias into sin omega t. where sin omega 0 t. Omega 0 is equal to 2 pi by capital T. So resulting oscillation amplitude is 2 by pi into I by S. So A is equal to 2 by pi into I by S into Rp. Because it will be taken across a resistor, so the drop in the resistor is to be taken into consideration, so that Rp will be multiplied. Variations on a theme, forget this is not required. Then we'll come to real oscillator. There are three types of oscillator which we are going to consider. One is Colpitts oscillator, one is Clapp oscillator, one is Hartley oscillator. I hope you have heard these names and you have already read these oscillators. So the Colpitts oscillator circuit is this. You have two capacitors and an inductor. The two capacitors are in series. Two capacitors are in parallel in series with the inductor. So this will be from the discrete designs. You should have read this. This has good phase noise. That is the advantage. But it is not apparent that this is an advantage of this design over negative resistance design of CMOS applications. Now, if you have the Colpitts oscillator, because this analysis will be using this analysis we will use in the other oscillators also. So what we will do is look at the circuit. The circuit is, we have two capacitors C1, C2 and L, and they are connected to the load to via RL, and what we will do is we will find out its equivalent circuit. So analysis of cap transformer used in the Colpitts oscillator. So use a transformer. So instead of directly connecting the load to capacitor, use a transformer. So what we are doing here is we are using a transformer. Through a transformer to the secondary of the transformer, the RL is used. Now if you use the RL to the secondary of the transformer, the turn ratio of the transformer is 1:n. So primary to secondary is 1:n. Then in that case, the equivalent value of the capacitance will be C1 parallel C2. So C1 parallel C2 means C1 into C2 divided by C1 plus C2. What will be N? N will be equal to C1 by C1 plus C2. N will be the number of turns will be determined as this, C1 by C1 plus C2. Then Rin is equal to 1 by N square into RL. That will be again equal to V out, whatever is the output voltage across the load L, across the inductor L. So V out will be the voltage across the inductor L. Then C1 in parallel with C2, equivalent of that capacitance. So L parallel with that C, then that parallel with Rin. So Rin is 1 by N square into RL. Here what we do is we assume that the impedances of the capacitance are less than RL at resonant frequency of the tank circuit. This simplifies, this analysis is simplified because of that assumption, and the ratio, this ensures that the ratio of V1 to V out is set by the capacitance and not by RL. RL does not affect the ratio of V1 to V out. Power conservation leads to transformer relationship shown above. Now simplified model of the Colpitts oscillator you based on the previous analysis. Left one is shows you the Colpitts oscillator, then its equivalent is shown on the middle one, then on the right top is its equivalent, then on the bottom is the final equivalent circuit. The purpose of capacitor transformer is it reduces the loading on the tank circuit and it reduces the swing at the source node. So if it reduces the swing at the source node, it stabilizes the circuit. So important particularly for bipolar transistors. If you are using bipolar transistors instead of the FET, then it is, or if you are using BJT, this is very important. The transformer ratio is set so that you get the best noise performance. The design of the Colpit oscillator, same thing as we have seen earlier. R equivalent only is here RP in parallel with 1 by Gm into N square, or RP in parallel with Rin. C is equal to C1 parallel with C2. These two are there. Then design first the tank circuit for high Q, then choose bias current, I bias, for large swing. So without going far into the GM saturation as in the previous case, that we will do. Then choose the transformer ratio for the best noise. Thumb rule is N is equal to 1 by 5 according to Tumley. Then choose transistor size to achieve the adequate large GM1. Now we will calculate the oscillator swing as a function of I bias. I1T, that consists of the pulses whose shape and width are a function of the transistor behavior and the transformer ratio. Usually these pulses are very narrow band. So approximately these pulses are narrow square wave pulses with width of W. A small W is very small. At fundamental component, it will have I1T will be equal to 2 times I bias into sin omega 0 t. Omega 0 as before is equal to 2 by capital T. A in this case also is equal to, no, in this case it is not I bias by 2, it is 2 times I bias into R equivalent. Earlier when we took the square wave, it was I bias by 2 into RP. And then the next oscillator is the Clap oscillator. In the Clap oscillator, you have three capacitance, one inductance, two inductances. Same as Colpit oscillator, except that the inductor portion of the tank is isolated from the drain of the device. This allows inductor voltage to achieve a larger amplitude without exceeding the maximum allowable voltage at the drain. This is good for achieving low phase noise. This is good for achieving low phase noise. Simplified model is this is exactly same as the Colpit oscillator, only careful with the parallel resonances. Otherwise, this is same as the Colpit oscillator. And then finally, we will come to the Hartley oscillator. In the Hartley oscillator, you have 2 inductors and 1 capacitor. It is just opposite of the dual of the Colpit oscillator. It has 2 inductors, 1 capacitor. Same as Colpit oscillator, but uses tapped inductors rather than series capacitors to implement the transformer portion of the circuit. This is not popular for So this is not popular for IC implementation because you have inductors. Inductors means it will take more space. Same equivalent circuit as the Colpit oscillator, similar to Colpit oscillator. Only thing is one should be careful about the parasitic resonances. Then instead of for these inductors, you can use the spiral inductors or lateral capacitor. This can be used, or bond wire inductors. So inductors and capacitor in the tank circuit can be lateral capacitors with high Q. Q greater than 50. Spiral inductors have moderate Q 5 to 10, but they are completely integrated and have tight tolerance less than plus minus 10%. Bond wire inductors, they have high Q more than 40, but not as integrated as have poor tolerance greater than 20%. integrated regenerator circuit. Forget this. This is not required. Water wave regenerator not required. Okay. And there are other types of regenerators like quartz crystal, SAW device, and MEMS device. These you can see. These are can be the only you remember the names. Quartz crystal. These have very high Q, very accurate and stable frequency, but the frequency is less than 200 megahertz. This is not integrated. So this is used to create low noise, accurate reference voltage. SAW devices, wide range of frequencies. This is cheap and this is particularly used in audio frequency. MEMS devices, they use cantilever beams. They promise high Q, but they are not tunable because the beam, once you design the beam is fixed, and they don't have the range up to gigahertz. So the regional frequency is below 1 gigahertz. Q is greater than 1000, but this is non-tunable and has poor accuracy. With that, we come to the end of today's discussion, today's lecture. We'll meet on Wednesday with when we'll continue something on this VCO. Then we'll go to other parts. So thank you for attending the class today. Sugar बढ़ गया उसका, बात तो खाइए, बात तो आलू, जिया ना कोई का, आलू सारू, जो आरो तरकारी देला करो, तरकारी पड़ती ना आलू की सारू, ना करे.